Welcome! In this session, we'll dive into an intriguing problem from LeetCode, problem number 73, set matrix zeros. This problem challenges us to manipulate a matrix in an efficient way while adhering to certain constraints. Stay tuned as we explore approaches to solve it, including a brute force method and optimized strategies. In this problem, you are given an m by n integer matrix, and your task is to modify it such that if any element in the matrix is 0, you set its entire row and column to 0. Importantly, this modification must be done in place, meaning you cannot use extra space for another matrix to store results. Let's look at an example to understand this better. Here, the input matrix is a 3 by 3 grid. Notice that there is a 0 at position matrix 1, 1. As per the problem requirements, we need to set the entire row and column corresponding to this 0 to 0. The resulting matrix becomes 1 0 1 0 0 0 1 0 1. Each affected cell is updated directly within the same matrix, adhering to the in-place constraint. To break this down further, the element at matrix 1 1 is 0, so we target both the row at index 1 and the column at index 1. Every element in that row and column is set to 0, resulting in the modified matrix shown. Now, consider a slightly larger example. Here, the input is a 3 by 4 matrix. This time, there are zeros at matrix 0, 0, and matrix 0, 3. Following the same approach, for each 0, we set its corresponding rows and columns to 0. The resulting matrix is 0 0 0 0 0 4 5 0 0 3 1 0. This demonstrates how the problem scales to larger matrices and handles multiple zeros effectively. Let's analyze the second example in more detail. The zeros at matrix 0, 0, and matrix 0, 3 influence the entire 0th row as well as the 0th and third columns. This means that every element in these rows and columns must be updated to 0. The modified matrix becomes 0 0 0 0 0 4 5 0 0 3 1 0. Now, let's review the constraints of the problem. The matrix will always have dimensions between 1 and 200 for both rows and columns, and each value in the matrix can range from -1 billion to +1 billion. These constraints highlight the need for a solution that is both space-efficient and capable of handling large matrices. Several edge cases must be considered for a robust solution. For instance, if the matrix contains only a single row or column, you need to ensure that zero propagation is handled correctly across that single row or column. If there are no zeros in the matrix, the output should remain identical to the input. Additionally, for very large matrices, such as 200 by 200 grids, your approach must be efficient while modifying the matrix in place. Finally, if multiple zeros exist in the same row or column, it is crucial to avoid overwriting intermediate updates, ensuring all affected rows and columns are properly set to 0 by the end of the process. To solve the problem of setting matrix zeros, we first considered a brute force approach. The idea here is straightforward: iterate through the matrix, and whenever a 0 is encountered, immediately set all elements in that row and column to 0. This method modifies the matrix directly as we traverse it. However, this simplicity comes with significant trade-offs. Modifying the matrix on the fly can lead to unintended consequences, like prematurely zeroing rows or columns that shouldn't be affected yet. Additionally, while the initial traversal takes m*n time, the repeated updates to rows and columns can lead to inefficiencies, potentially pushing the time complexity to m times n squared, in the worst case. On the plus side, this approach uses no extra memory, but the inefficiency and potential for side effects make it less practical for larger matrices or time-sensitive applications. Next, we explored an approach that uses additional memory to avoid the issues with in-place modification. The key idea here is to use two marker arrays, one for rows and one for columns, to keep track of which rows and columns need to be zeroed. The process involves two main steps. First, traverse the matrix to identify all 0 elements and mark their corresponding row and column in these arrays. Then, make a second pass through the matrix, and for each element, check if its row or column is marked. If so, set the element to 0. This method eliminates the risk of premature updates and is more efficient, with a time complexity of m*n due to the two traversals. However, it requires m plus n additional space for the marker arrays, which could be a limitation for very large matrices or constrained environments. While this approach is easy to implement and avoids some pitfalls of the brute force method, the added memory requirement makes it less ideal when an in-place solution is preferred. The most efficient approach we considered is an optimized in-place solution that eliminates the need for extra memory while maintaining M**n time complexity. The intuition here is to use the first row and first column of the matrix itself as markers to track which rows and columns need to be zeroed. To avoid disrupting the original data prematurely, we also use two flags to determine whether the first row and first column should be zeroed. The steps involve first traversing the matrix and using the first row and column as markers whenever a zero is encountered. Then, in a second traversal, we use these markers to set the appropriate cells to zero. Finally, we check the flags to handle the first row and column separately. This approach is space efficient, requiring no additional arrays, and is computationally optimal. However, it does require careful implementation to ensure the first row and column are handled properly without overwriting data too early. Despite this complexity, it strikes the best balance between space and time efficiency. We ultimately chose the optimized in-place solution as our strategy, as it provides the best balance of efficiency and practicality. While the brute force approach is simple, its inefficiency due to redundant updates makes it unsuitable for large matrices. Similarly, although the additional memory approach is easier to implement and avoids premature modifications, it does not meet the problem's in-place constraint. The optimized in-place solution stands out because it avoids extra memory usage while maintaining an M**n time complexity. Key insights that led to this choice include recognizing that the matrix itself can act as a marker, which eliminates the need for additional space, and that handling the first row and column separately ensures no premature overwriting. This method, while slightly more complex, is the most effective for solving the problem within the given constraints. The optimized in-place solution offers significant advantages, but it does involve some trade-offs. On the positive side, it minimizes space usage, making it suitable even for large matrices, and avoids the inefficiencies of redundant updates seen in the brute force method. Additionally, it meets the in-place constraint, unlike the approach that uses additional memory. However, it requires careful handling of edge cases, such as when the first row or column contains zeros, to ensure the solution works correctly without disrupting the process. Overall, this approach is the best choice as it balances time efficiency, space constraints, and problem requirements, making it a robust and practical solution for the set matrix zeros problem. The problem asks us to modify a given 2D matrix such that if any cell contains a zero, all elements in its corresponding row and column are set to zero. The challenge is to do this efficiently, minimizing space usage. To achieve this, the algorithm is broken into distinct steps. First, we need to identify all the zeros without directly modifying the matrix. This is crucial because altering the matrix during traversal can cause cascading changes, making it difficult to correctly locate other zeros. To handle this, we use two data structures, specifically sets, to record the rows and columns that need to be zeroed out. By traversing the entire matrix once, we can identify all zero elements and store their respective row and column indices in these sets. This setup ensures our modifications are accurate and isolated from cascading issues. After identifying the rows and columns to be modified, the next steps involve using the sets to zero out the appropriate rows and columns. For rows, we iterate through each index stored in the 0_rows set and set all elements in those rows to zero. This is done with a straightforward loop that overwrites each element in the row. Similarly, for columns, we perform the same operation using the indices stored in the 0_col set, zeroing out all elements in the corresponding columns. By separating the zeroing process into distinct phases for rows and columns, we ensure that the original structure of the matrix remains intact during the modification process. After completing these operations, the matrix is fully updated, and we can return the modified result. This approach, while effective, does utilize additional space for the sets 0_rows and 0_cols, which requires M+n space where m is the number of rows and n is the number of columns. However, this is significantly more efficient than using an auxiliary matrix of size M**n. Additionally, the algorithm is designed to handle various edge cases. For example, if no zeros are present in the matrix, it simply returns the matrix unchanged. If all elements are zeros, the entire matrix remains zero. Single row or single column matrices are also handled gracefully without errors. The key data structures here are the sets, which allow efficient lookups and prevent duplicate entries. This avoids redundant operations, ensuring the algorithm runs efficiently. In terms of complexity, the algorithm is efficient. The time complexity is O(m*(n), which comes from the two traversals of the matrix, one to identify the zeros and another to modify the rows and columns. The space complexity is O(m+n), attributed to the additional space used by the sets 0_rows and 0_calls. This trade-off between time and space allows the algorithm to remain efficient while staying manageable in terms of memory usage. To solidify our understanding, consider an example matrix. Suppose the input matrix is 1, 2, 3, 4, 0, 6, 7, 8, 9. This example highlights how the algorithm identifies zeros and modifies the matrix step by step. In this example, during the identification phase, we find a 0 at position 1, 1. This means row 1 and column 1 need to be zeroed out. We record these indices in the 0_rows and 0_calls sets. Next, we proceed with modifying the rows. For 0_rows equals 1, we set all elements in row 1 to 0, resulting in the intermediate matrix 1, 2, 3, 0, 0, 0, 7, 8, 9. After modifying the rows, we move on to the columns. For 0_calls equals 1, we set all elements in column 1 to 0, transforming the matrix into 1, 0, 3, 0, 0, 0, 7, 0, 9. At this point, the algorithm has completed all required modifications. Finally, the output matrix is 1, 0, 3, 0, 0, 0, 7, 0, 9. This result demonstrates the correctness of the algorithm, as all rows and columns containing zeros in the original matrix have been appropriately zeroed out. The separation of the identification and modification phases ensures accuracy, while the use of sets minimizes redundant operations. This approach strikes a balance between simplicity and efficiency, making it a robust solution for the problem of setting matrix zeros. Here, we start by defining a class called solution and a method named setZeros that takes a matrix as its input. The first step is to determine the dimensions of the matrix, which we store in rows and calls. Then, we check if the first row or the first column contains any zeros. This is done using the any function, which iterates through the respective row or column. If a zero is found, we set flags first_row_has_0 and first_call_has_0 to true. These flags will help us decide later whether the first row or column needs to be zeroed out. Next, we use the first row and first column as markers for the rest of the matrix. This means that whenever we encounter a zero in a cell that is not in the first row or column, we mark the corresponding positions in the first row and column as 0. This marking process helps us keep track of which rows and columns need to be zeroed without using extra space for additional arrays. After marking, we iterate through the matrix starting from the second row and second column. For each cell, if its corresponding row or column marker is 0, we set the cell to 0 as well. This ensures that all the necessary cells are updated based on the markers. Finally, we handle the special cases for the first row and first column. If the first_row_has_0 flag is true, we iterate through all columns of the first row and set each cell to 0. Similarly, if the first_call_has_0 flag is true, we iterate through all rows of the first column and set each of their first cells to 0. This ensures that the first row and column are correctly updated based on our earlier checks. By using the first row and column as markers, we achieve the goal of setting the appropriate rows and columns to 0 efficiently, without needing extra space for auxiliary storage. Here, we begin by importing the necessary packages and defining our class and method. The setZeros method takes a two-dimensional integer array, matrix, as input. First, we determine the number of rows and columns in the matrix using matrix.length and matrix0.length. Then, we declare two Boolean flags, first row has 0 and first call has 0, which will help us track if the first row or the first column contains any zeros. This is important because we'll use the first row and column later to mark which rows and columns need to be zeroed. Next, we iterate through the first row to check if any of its elements are 0. If we find one, we set first row has 0 to true and break out of the loop. Similarly, we loop through the first column to check for zeros, updating the first col has zero variable as needed. These checks ensure that we don't lose track of the original state of the first row and column as we modify the matrix later. Now, we leverage the first row and column as markers to efficiently identify which rows and columns need to be zeroed. Starting from the second row and second column, we iterate over the matrix. Whenever we encounter a zero in the matrix, we set the corresponding cell in the first row and the first column to 0. This marks the entire row and column for future processing. Once marking is complete, we proceed to zero out the appropriate cells in the matrix based on these markers. Again, starting from the second row and column, we check if either the corresponding cell in the first row or the first column is 0. If so, we set the current cell to 0. This approach avoids the need for additional space since we're using the first row and column of the matrix itself to store our markers. Finally, if the first row has 0 flag is true, we zero out all elements in the first row since it was marked earlier. If the first col has 0 flag is true, we zero out all elements in the first column. This is the final step to ensure the matrix is correctly updated based on the original zeros, while preserving the integrity of the first row and column during processing. By the end of this method, the matrix has been modified in place to meet the problem's requirements. This implementation is efficient, using constant extra space aside from the input matrix and the two Boolean flags, while maintaining a time complexity of O, m*n, where m and n are the dimensions of the matrix. The method is now complete, and the matrix will reflect the desired state with all necessary rows and columns set to 0. To solve this problem, let's start with a basic example. We are given a 3x3 matrix, and the goal is to set the entire row and column to 0 wherever a 0 is found in the matrix. First, we check if the first row or first column contains any zeros. Here, neither the first row nor the first column has a 0, so both flags first_row_ has _0 and first_col_ has _0 are set to false. Next, we iterate through the rest of the matrix starting from the second row and second column. When we find a 0 at matrix 1, 1, we mark its row and column by setting the corresponding elements in the first row and first column to 0. After this marking step, the updated matrix looks like this. The first row now has a 0 at matrix 0, 1, and the first column has a 0 at matrix 1, 0. This prepares us for the next step of updating the rest of the matrix based on these markers. Using the markers from the previous step, we now update the matrix. As we iterate through the matrix again, we skip the first row and column and look at the inner elements. At matrix 1, 1, the marker in its row and column indicates that it should be set to 0, so we update it. Similarly, at matrix 1, 2, its row marker from the first column is also 0, so a 2 gets updated to 0. Finally, at matrix 2, 1, its column marker from the first row is 0, so it is set to 0 as well. After these updates, the matrix now reflects the correct rows and columns set to 0 based on the initial 0 location. The updated matrix is almost complete, with the exception of any changes to the first row or column, which we handle next. Now we check if any changes are needed for the first row and the first column. Since both first_row_ has _0 and first_col_ has _0 are false, no modifications are required for either the first row or the first column. Therefore, the matrix remains as it is. The final output matrix is fully updated and looks like this. All zeros are set correctly based on the initial conditions. With this, the problem is solved for this basic case. Let's move on to a more complex case where zeros are present in the first row and first column. In this new example, we start with a matrix that has zeros in both the first row and the first column. First, we determine that first_row_ has _0 is true because there's a 0 in the first row at matrix 0, 0. Similarly, first_col_ has _0 is also true because the 0 at matrix 0, 0 is in the first column as well. Next, we iterate through the matrix, excluding the first row and column, to mark zeros. At matrix 2, 1, we find a 0, so we mark its row and column by setting matrix 2, 0, and matrix 0, 1 to 0. After this marking step, the first row and first column now indicate which rows and columns need to be set to 0. The updated matrix reflects these markers, and we are ready to proceed with updating the rest of the matrix based on them. Using the markers, we now perform updates to the matrix. Starting with matrix 1, 1, its row and column markers indicate it should be set to 0, so we update it. At matrix 1, 2, there's no marker indicating a 0, so it remains unchanged. At matrix 2, 1, the marker in its row indicates that it should be set to 0, so we update it as well. After completing these updates, the matrix now has the correct rows and columns updated based on the markers. Finally, we ensure that the first row and the first column are updated as well, since both first_row_has_0 and first_col_has_0 are true. This means we set the entire first row and first column to 0. The final matrix is now fully updated and looks like this. All required rows and columns have been set to 0. After completing all updates, the final output of the matrix for this example is as follows. The first row and first column are zeros, and all other rows and columns reflect the correct updates based on the initial zeros in the matrix. This example demonstrates how the algorithm handles cases where zeros are present in the first row and first column, requiring additional updates to handle these special cases correctly. Lastly, let's look at an edge case where the matrix has only a single row. Since there's a 0 in the first column of this single row at matrix 0, 0, both first_row_has_0 and first_col_has_0 are true. However, because there is only one row, there's no need to iterate for marking or updating based on markers. Instead, we directly set the entire first row to zeros because first_row_has_0 is true. The final matrix now consists of all zeros, as expected. This highlights how the algorithm efficiently handles edge cases with minimal computation when the matrix has only one row or one column. The time complexity of this solution is O, m*n, where m is the number of rows and n is the number of columns in the matrix. To understand this, let's break it into distinct steps. First, we initialize two flags to determine whether the first row or the first column contains any zeros. To do this, we iterate through all n columns of the first row, which takes O, n, and similarly, we iterate through all m rows of the first column, which takes O, m. Together, initializing these flags takes O, m plus n, time. Next, we move on to marking the rows and columns that need to be zeroed. This is done by iterating through the submatrix, meaning all rows except the first and all columns except the first. Here, two nested loops are used, one for the rows and one for the columns, resulting in m1*, n1 iterations, which simplifies to O, m*n. After marking, the next step involves zeroing the appropriate cells based on the markers placed in the first row and column. This also involves iterating through the submatrix with two nested loops, one for rows and one for columns, leading again to O, m*n iterations. Finally, we handle the first row and first column separately. If the first row contains a 0, we iterate through all n columns to set them to 0, which takes O, n. Similarly, if the first column contains a 0, we iterate through all m rows to set them to 0, which takes O, m. When you combine the time for these steps O, m plus n, for flags, O, m*n, for marking, O, m*n, for zeroing, and O, m plus n, for handling the first row and column, the total time complexity is dominated by the O, m*n terms, making the overall time complexity O, m*n. The space complexity of this solution is O1, meaning it uses constant extra space regardless of the size of the input matrix. This is because the algorithm modifies the input matrix in place without using any additional data structures. The space used by the matrix itself doesn't count towards the algorithm's space complexity since it is part of the input. Additionally, the solution uses only two extra variables, first_row_has_0 and first_col_has_0, to track whether the first row or column needs to be zeroed. These variables occupy constant space, O1. There are no auxiliary arrays or temporary matrices used, as the algorithm cleverly utilizes the first row and first column of the input matrix to store markers, avoiding the need for any additional storage. Consequently, the total space complexity is O1, as the algorithm only uses a few constant-sized variables. To put this into perspective, consider a brute force approach. A naive solution would involve creating a separate copy of the matrix, iterating through all cells to identify zeros, and then modifying the corresponding rows and columns in the new matrix. While this approach achieves the same time complexity of O, m*n, it requires m*n additional space for the auxiliary matrix. In contrast, the optimized solution dramatically reduces space complexity to O1 by reusing the input matrix for marking rows and columns. This makes the optimized solution much more memory efficient, particularly for large matrices. To further validate the time complexity, consider the mathematical reasoning. The core of the algorithm involves nested loops over the matrix dimensions m and n. Each iteration of these loops performs constant time operations, such as comparisons or assignments. The outer loop iterates over the rows, contributing O(m), while the inner loop iterates over the columns, contributing O(n). Together, the nested loops yield O(m*n) iterations. Smaller operations, such as flag initialization and handling the first row and column, add at most O(m+n), which is insignificant compared to O(m*n) for large matrices. Therefore, the overall time complexity is dominated by O(m*n). Additionally, because the algorithm processes the entire matrix regardless of its initial state, the time and space complexities remain consistent across best, average, and worst cases. This consistency results in O(m*n) time complexity and O(1) space complexity for all scenarios. One of the most common mistakes when solving the set matrix zeros problem is immediately modifying the matrix as you iterate through it. This approach can create issues because setting a 0 in one cell might unintentionally trigger zeros in other parts of the matrix. To handle this, it's important to use placeholders such as temporary arrays or markers to first track where the zeros should go, then make the actual modifications in a second pass. Another frequent error is overlooking edge cases, such as matrices with a single row or column, or matrices that contain no zeros at all. These scenarios can result in bugs like index out-of-bounds errors or unexpected behavior. A good practice is to test your solution with a variety of edge cases, including small or empty matrices, to ensure robustness. Another pitfall is overusing extra space by relying on large auxiliary data structures, such as full-size temporary matrices, to track zeros. While this approach works, it unnecessarily increases space complexity and may fail in scenarios where memory is constrained. Instead, aim for an optimized solution with O(1) space by using the matrix itself as a marker or carefully utilizing additional rows and columns. On the same note, incorrect marker usage can also lead to problems. For instance, confusing markers with actual zeros in the matrix can cause unintended propagation of zeros. To avoid this, consider using unique markers, like a value of -1, or dedicating an extra row or column specifically for tracking. Finally, hardcoding matrix dimensions or assuming uniform sizes can break your solution for non-square or dynamically sized matrices. To ensure flexibility, always write your code to handle any m(x)n matrix, regardless of its dimensions. This problem is often used in interviews to test your ability to recognize patterns and efficiently propagate changes across a 2D matrix. Specifically, it challenges you to identify where zeros should be placed and apply those changes systematically. Interviewers typically expect candidates to improve space complexity, transitioning from an O(m+n) solution to O(1). It's also important to articulate the trade-offs between readability and optimization. For instance, while temporary arrays may make the solution easier to understand, in-place marking reduces space usage but requires more careful handling. Discussing edge cases proactively can further demonstrate a thorough understanding of the problem. Additionally, highlighting how this problem relates to other matrix traversal or state propagation problems shows that you can generalize solutions across different scenarios. This problem is directly related to other matrix manipulation challenges on LeetCode. For example, in LeetCode 48 Rotate Image, you also work with constraints to modify a matrix in place. Similarly, LeetCode 289 Game of Life involves propagating states across a matrix, while LeetCode 36 Valid Sudoku requires processing a 2D grid under specific rules. When solving set matrix zeros, there are also alternative approaches to consider. Using temporary arrays to track rows and columns that need to be zeroed is simple and intuitive, but it incurs an O(m+n) space cost. On the other hand, in-place marking uses the first row and column of the matrix to store markers, achieving O(1) space complexity. However, it requires extra care to avoid overwriting original data, making it slightly more complex to implement. Another approach to solving this problem is bit masking, where you use a compact representation to track which rows and columns need to be zeroed. While this method reduces memory usage, it introduces additional complexity and might not be intuitive during an interview. Recursive backtracking is another theoretical option, where zeros are propagated recursively from each zero element. However, this method has high time complexity and is impractical for large matrices. It's generally not recommended for implementation but can be useful for brute force validation or discussing the problem from a theoretical perspective. Each approach has its trade-offs, so it's important to choose one that balances simplicity, efficiency, and the specific constraints of the problem. Thank you for joining me in solving set matrix zeros. We reviewed both brute force and efficient approaches, emphasizing the importance of optimization. Keep practicing similar problems to enhance your skills, and don't forget to like, share, and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!